For a reaction for which delta H equals negative 64.2 kilojoules per mole and delta S equals 285 joules per mole per Kelvin, which of the following statements is true? In order to answer this question, we need to remember that the Gibbs free energy change is equal to the delta H minus T delta S. And think about the signs on the delta H and the delta S. So in this problem, we have a negative delta H, the negative 64.2. And for the delta S, we have a positive value, the 285 joules per mole per Kelvin. And we have this negative in the equation, which is going to get multiplied times that positive delta S. And so in this case, because this will always be negative, anytime you multiply a negative times a positive, you get a negative number. So we're always going to end up with the negative delta G, because you're taking a negative number and you're subtracting something from it. So no matter what you do at any temperature, you're going to have a negative delta G, always. Okay? Now what that means is that has some consequences to it. That means that it's spontaneous at all temperatures. Okay? And the other thing to remember is that you will never have a delta G equal to 0. Never. And the reason why is because in order for something to go from non-spontaneous to spontaneous, or in the opposite direction, spontaneous to non-spontaneous, you have to pass through 0. Well, because this is always going to be spontaneous, it will never go through 0. And the other important thing to remember about a delta G that's equal to 0 is that is when you reached equilibrium. Delta G equals 0 at equilibrium. So the true statement here is going to be C. The reaction will never reach equilibrium because the delta G will never equal 0. So it doesn't matter which temperature that you pick. In this particular problem, they throw out their 225 Kelvin. But we determined that it's spontaneous at all temperatures because we have a negative delta H and a negative T times delta S. So those two can't be true. And the reaction is never at equilibrium. So that's not true of any chemical reaction. It starts at some non-equilibrium situation and then reaches equilibrium. But in this case, it will never reach equilibrium. So this is one of those weird cases in chemistry. Even though most chemical reactions are reversible and do achieve some sort of equilibrium, this is one of those reactions that's one directional, kind of like combustion, or even like an explosive reaction that just goes in one direction and is not a reversible reaction.